In a previous video, we derived the characteristic roots for a second-order differential equation. And in this, we found that the eigenvalues, or the characteristic roots of the second-order equation, are given by the negative value of the damping ratio times the natural frequency, plus or minus the natural frequency times the square root of the damping ratio squared minus 1. So now we're going to take a quick look at the different possible values that this characteristic root can take on. So if we rewrite our solution to the quadratic equation, where we come up with the values of the characteristic roots, or the eigenvalues, again, we'll take a look at a couple of possibilities that we can have. Okay. So our eigenvalues, or our characteristic roots, can take on a couple of different cases, and the couple of different cases that we're going to be interested in depend upon the value of the damping ratio. Remember that the damping ratio is given by the damping of the system divided by 2 times the square root of the stiffness times the inertia of the system. Right, so if we can come up with our general second-order differential equation and determine what the values of the inertia, the stiffness, and the damping are, we can calculate the value of the damping ratio. So we have 3 possible cases that we need to be worried about with the damping ratio. And it all involves this term under the radical right here. Okay, so the first case that we're going to look at is what happens if the damping ratio is greater than 1. Well, if the damping ratio is greater than 1, then our eigenvalues, the term under this radical is going to be a positive, and we can take the square root of that, multiply it by the natural frequency, and in that case we're going to have a real value that can be added or subtracted from this value, which is the damping ratio times the natural frequency. So if our value of the damping ratio is greater than 1, in this case we're going to have 2 distinct eigenvalues, or 2 distinct characteristic roots. Alright, where there's a lambda 1 and a lambda 2. Alright, and lambda 1 is going to be negative squiggle omega n plus omega n times the square root of squiggle square root minus 1. And lambda 2 is going to be the same thing, except we're going to subtract that value. Alright, this is a special case, or one of the cases of our solutions, which we're going to call the overdamped case. Okay, so in this case we have 2 distinct, and I need to put in another word here, real characteristic roots. Alright, in this case we're going to get an overdamped system, and we'll look at how these overdamped systems behave in a little bit. The next case that we have to worry about is if the damping ratio is identically equal to 1. If the damping ratio is identically equal to 1, then this term under the radical becomes 0. Alright, and we have 0 to add or subtract to the damping ratio times the natural frequency. In that case, we have real roots, but the 2 solutions that we have, it'll be plus 0 and minus 0, so they're repeated. Alright, in that case, lambda 1 is equal to lambda 2 is equal to lambda. So they're all the same value, and they're all equal to the damping ratio times the natural frequency. But since the damping ratio is 1 in this case, it's equal to the natural frequency. And this is a case that we're going to call critically damped. Critically damped. All right, and we'll look at the behavior of critically damped systems in a little bit as well. And, of course, you can probably guess it now. If the damping ratio is less than a value of 1, then something interesting is going to happen. If the damping ratio is less than 1, the value under the radical is going to be less than 1 as well, because we're going to have a value smaller than 1, and we're going to subtract 1 from it. So we're going to wind up with an imaginary value on this side of our eigenvalue. All right, so what I'm going to do is I'm going to slightly rearrange this. And the way I'm going to rearrange this is I'm going to say that our characteristic root is equal to negative squiggle omega n plus or minus. Now I'm going to take the natural frequency, and I'm also going to multiply it by the square root of negative 1. So I'm going to pull that negative 1 out, and then multiply it by the square root of 1 minus the damping ratio squared. Okay? All right. We all know from our studies of math that the square root of negative 1 is the imaginary number. In this class, we're going to call the imaginary number, we're going to denote it with a j. So we'll have omega n j, and the reason we use a j is because I is traditionally used for current, so j is going to represent our imaginary number. All right, times the square root of 1 minus squiggle squared. All right, and then what I'm going to do is I'm going to define a different variable. I'm going to define something called the damped natural frequency. All right, so W sub d is going to be the damped natural frequency, and I'm going to define that as omega n times the square root of 1 minus the damping ratio squared. All right, so in that case, my eigenvalues are going to wind up being negative squiggle omega n plus or minus the imaginary number times omega sub d. All right, and in this case, I see that I'm going to have a real number plus or minus an imaginary number. All right, and again, from our mathematics, we understand that that is something, a special number called a complex number. And since we have the same real component and either a positive value or a negative value of the imaginary component, we call that a complex conjugate. So our roots are complex conjugate characteristic roots. And in this case, this is the case where we are going to call this underdamped. And this is the case where we're going to see oscillatory behavior. We're going to see the bouncing back and forth that we did with our mass spring damper system that we looked at a few videos back. So this is the case where we're going to expect to see oscillations, and the overdamped case is where we're going to expect to see a slow approach back to the steady state value. And the critically damped case, when the damping ratio is equal to 1, is the transition point between these two, between the overdamped no oscillations case and the underdamped oscillations case. This critically damped right here is a theoretical condition. We can design systems that are close to critically damped, but the realities of the system are going to make them either fall in the underdamped category, the slightly underdamped category, or the slightly overdamped category. All right, so next we're going to look at the mathematical behavior and what happens when how we solve these different conditions.